Welcome back, ladies and gentlemen. JTolan Media1 put out a video this afternoon from the Californian aqueduct. I haven't spoken to this guy for about 5 months since he did a drive-by comment on my Californian aqueduct video, pretty much casting doubt on any and all elevation numbers because apparently they prove the globe. Anyway, as usual, his videos are pretty scant on details like observer location. So I had to employ some NASA spies to follow him around for a little while. As it turns out, his observer location was along this path. He took various photos from various heights. Here's the latitude and longitude for the car park if you'd want to check it out. And just to make sure that it is actually the location, here it is being faded in and faded out on Google Earth. You'll actually notice in the background up the top here that the distant mountains are appearing a little higher. Obviously that's because of refraction, which Google Earth does not implement. Alright, so let's have a listen to the main point of JTolan's video.
So in the inset, you see I have an analysis of the angles to the distant mountain, and it's actually a delta in elevation. So my observation was from 3,200 feet, and so the delta is 1,700, and I calculate the angle, vertical angle, theta 1, and then I do the same thing for the quartzite mountain. And notice the angles are pretty close, off by 0.08 milliradians.
Yep, so what he's saying here basically is that this mountain in the background should appear pretty much exactly the same height as Quartzite Mountain, maybe 1 or 2 pixels higher.
So it is also, it should come out slightly higher than the Quartzite Mountain for the vertical analysis and the trigonometry, but it's way below.
Correct. I wonder if that's because you're assuming a flat plane to do your trigonometry. Anyway, let's do some pixel counting and see if we can figure out if this observation matches the globe or a flat Earth. So first of all, I had to work out the exact observer location, and as I said, I got my NASA spies onto it, and that's pretty accurate. Secondly, I had to pick out a couple of landmarks here in order to derive an angular size scale. I picked this little landmark here, which is kind of like a bunch of rocks. This is its location. This is its heading from the observer location. And on my screenshot that I took, the X pixel coordinate was 61. Then I went to Quartzite Mountain, the main tower on Quartzite Mountain. Here again are its coordinates, the heading from the observer location, and its X pixel on the screenshot. So with those 2 data points, we can derive an angular size scale, and on this particular screenshot, 488 pixels is the equivalent to 1.12 degrees. Right, so now what I wanted to work out was exactly how much the differential is between Quartzite Mountain and this mountain in the background, and it turns out to be 36 pixels on my screenshot, and that equates to 0.083 degrees. So this is how much in reality this mountain appears lower than Quartzite Mountain. I remember that JTolan Media on his flat Earth trigonometry expected this background mountain to actually be a tiny bit higher than Quartzite Mountain. Right, so I have my whiz-bang spreadsheet that I made a couple of years ago. Unfortunately, it is in metric, but in any case, I've put in the values that JTolan put on his screenshot. So 3,200 feet observer location, 975 meters, 4,500 feet for Quartzite Mountain, 53 miles, 4,900 feet for the distant mountain at 68 miles, and then it does some calculations whether it assumes a flat Earth or a globe. So you can see on a flat Earth, the elevation angle that you're looking up to that mountain should be 0.266 degrees, which is this one. And the distant mountain should appear very, very slightly higher. So 1/200th of a degree higher. So almost nothing. On a globe, however, you should be looking down to Quartzite Mountain by 0.06 degrees. And you should be looking further down to the more distant mountain at minus 0.15 degrees. And that is a difference of 0.088 degrees. And if you remember back 1 minute, the angle that we actually measured was 0.083 degrees. So score 1 for the globe and 0 for flat Earth trigonometry.
So the geometric analysis does not explain the observed image compression. Something else is going on. And that's the exciting part, folks. That's the really exciting part. So what's really going on? Well, as you probably guessed it, there is some refraction that's occurring. But is it only atmospheric? Or is there something else?